All right. So now that we've looked at atomic structure and electron orbitals, let's look at some of the basics of bonding, some of the things that are going to help us talk about ionic covalent bonding. All right. So most ceramics, and that's going to be, again, the focus of this class. So we're looking at um, ceramics, and they have some degree of ionic character. So that means some degree of ionic bonding. And so that means the exchange of electrons, and that's going to be important. So two terms that we're going to see a lot then, if we're looking at exchange of electrons, is ionization energy, sometimes abbreviated as IE, and that's the energy that's needed to basically remove an electron from an element. So it's going to take some energy to rip off an electron from this element. So that's ionization energy. It creates an ion left behind. The other one is going to be electron affinity. And so that's a measure of an element's willingness to accept an incoming electron. So its affinity for that incoming electron. And so this can actually be positive or negative, but a lot of times this is positive energy. So both of these terms are going to be important because we are going to create positive ions, but we also have to create negative ions. And so both of these terms are equally important when we're looking at ionic character. So if we want to be able to approximate the fraction of ionic character, we can look at the electronegativity. So if you remember back to basic chemistry and basic bonding, electronegativity was the factor that contributes to how much ionic character we have, right? The further apart the electronegativity values are, the more ionic it is, and then the closer they are together, the less ionic, the more covalent in other types. And so this equation is basically a manifestation of that general rule of electronegativities. So the ionic character, or IC, is what you see here, 1 minus the exponential of minus 1/4. And then this represents the electronegativity of the metal, minus, and this could also be cation, minus the electronegativity of the nonmetal, or anion, and that's squared. So this just manifests the prediction of how much ionic character a compound of MX will have based on how different the electronegativity values are. And so this is something that you might have seen in MSE 201. So let's work an example of this to kind of get an idea of the percentages and what ionic character a material tends to have. So this is a chart of the electronegativities down here. One quick rule of thumb, if you are using electronegativity values, make sure you use values from the same source. So if you're going to use sodium and chlorine, make sure that they're from, for example, this, or if you're going to pull them from another resource, make sure they're both from the same source, because there are differences in electronegativity values. So go ahead and calculate this. This will be in the quiz for the week. So whenever we have questions like this embedded in the lectures, you can go find them in the quiz for the week, and make sure that you put your answer in the quiz. So take a minute, pause the video, see if you can calculate this real quick, and then we will come back and kind of go over the results of this and talk about what that means. All right, so hopefully you've had time to look at calculating this ionic character for sodium chloride. And we use this because sodium chloride is kind of thought as the prototypical example of ionic character. So all we're going to do, the really only values we need are the electronegativity values for the metal, or cation, which is sodium, and we need the electronegativity value for the anion, or nonmetal, which is chlorine. So for let's start with sodium. So sodium's over here. That has a value on this table of 0.9. If you used a different resource, you might get a slightly different value there. And then for chlorine, over here on the nonmetal side, it's 3. So if we plug those two values, 0.9 and 3, into this equation, and I'm not going to kind of go through the work. I think you can figure that much out. We get a ionic character of 0.67, or if you put that in a percent, it is 67%. So basically, what this is telling us is that this compound, sodium chloride, which you've probably seen a lot about as an ionic material, is 2/3 ionic. So what that tells us is it still tells us that there's a fair degree of other types possible. So even the most ionic bonds can have some other degree of covalency or metallic bonding, etc. So, we often think of these drastic terms of ionic compounds or covalent compounds or metallic compounds, but there's always a degree of the other mixed bonding. And so always keep that in mind, that there can be a mix of those two. All right, so again, electronegativity kind of gets us this ionic character and tells us, dissimilar atoms, which ones attract electron. And so it's basically a measure of the strength of an atom to attract electrons. So these over here in the top right over here with the highest numbers are the most likely to attract electrons. Then these over here with the smallest numbers are the least likely. So these are the most electropositive. These are the most electronegative because these attract, and so negative would be electrons. Positive because they get rid of electrons. So the general trends here is it goes up from left to right, and it goes up from bottom to top. All right. Another factor I want to kind of discuss, because this fits in well with the idea of the orbitals, but also of electronegativity, is an idea of shielding. And so shielding is the shielding effect is basically makes the energy to remove an electron easier, because if you think of an atom as a central positive core, the nucleus, surrounded by electrons, if we look at the outermost electrons, that outermost electron could be shielded from the positive charge, which it's attracted to, by inner electrons that kind of, again, shield the charge. So a shielding effect will make the energy to remove an electron easier. And so the results you kind of see are that ones up here, so again, periodic table, there's less shells as you go up. So n equal 1, 2, 3, 4, etc. So ones up here don't have as many electrons and therefore can't shield as much. And so you see that the ionization energies are much higher at the top, and then they go down as you can have more shielding effects when you have more inner electrons. So that's the general rule, but we also have to consider the specific orbitals. So I showed you these various orbital shapes, and that orbital shape will matter as well. So the s orbitals are all spherical in nature. So you can see where the electrons are located. So predominantly very close to the nucleus for 1s, further apart, further away, and the 2s kind of forms a shell, and then there's some in the middle too. And then the 3s, those are even further out in majority. So the ones closer to here shield very well electrons that may be further out in other shells. So this is the best, in terms of shielding. And then they shield the charge of the 2s better, and etc. So s orbitals, because they are so kind of dense, are very good at shielding for other electrons and other orbitals, but themselves are not very shielded by something else, if that makes sense. So in this case, they're better at shielding for other orbitals, but they don't get shielded well themselves. All right, so all of this talked kind of about the electron orbitals and the quantization of electrons, I want to kind of mention some of the things that's going to be important for as we move forward in the semester in our discussion of ceramics. First example of this is electron transitions. So we're talking about electrons moving from one position to the next. So any of these kind of green orbitals moving from one to the next, because energy is quantized, it has specific values, and that specific value can be tied to its energy. And so if we are able to witness, for example, that transition via energy, and energy in the form of X-rays, we can actually use that to identify what types of elements we have. So this is basically energy dispersive X-ray spectroscopy, EDS or EDX, and this is using those transitions, those quantized transitions, to measure the energy, which can then tell us what element. So iron here. So we have iron in the sample because we can witness the energy of the X-ray of an electron going from one position to the next in iron. It's going to have a very specific value going from this orbital to the next orbital. Same thing with any of the other elements. And so this is used in analyzing the chemistry of ceramics. We can also, the same transitions in different energy levels can also give us coloration in ceramics. So quartz, for example, if it's very, very pure, is either clear or opaque. So it doesn't have color associated with it. But if we have small amounts of impurities, they can result in very different colorations of the same basic material, quartz. And so those differences basically are a result of these transitions. So we have metal ions that result in photon transitions from different electron positions. And so those impurity elements in very small amounts can cause these colorations because it gives us energy at a specific wavelength, which is tied to visible light. And so we'll look at this later in the class when we get to optical properties. And again, these transitions can also be used to identify chemistry through another X-ray photoelectron spectroscopy. And this is, again, using transitions to determine the chemistry of a material. This just happens to be more surface sensitive.